New technology is helping us overcome the world's toughest challenges. And as technology's new pioneers, you need all of the tools, platforms, and resources to move innovation where it has to go. To drive us toward a safer, cleaner world. With advanced power and sensor solutions for electric and autonomous vehicles, allowing you to see, hear, and feel the road ahead. Our industrial and cloud power solutions are advancing robotics and helping to build clean, energy-efficient innovations for a data-driven world. With smart buildings and smart factories, we are creating new, connected ecosystems, ones where a healthy bottom line and a healthy planet are achieved the exact same way. At ON Semiconductor, we provide talented engineers with the creative solutions and the tools to meet the world's greatest challenges. Because now, having the right tools matters more than ever. The world will move wherever we take it. So, where to next? You bring the talent, we bring the tools.
Hello, and welcome to today's On Semiconductor Embedded World webinar on Power over Ethernet and Connected Lighting. In this webinar, we will learn about the latest news from the Ethernet Alliance and the emerging Connected Lighting and VLC technology. We will also explore what can make or break a PoE system. I'm Chris Kosters with On Semiconductor, and I'll be your moderator today. At the end of the webinar, we will be holding a Q&A session to answer any questions you may have. During the webinar, you can type your questions into the chat box on your right, and we will answer them at the end of the webinar. This webinar will be recorded and posted at onsemi.com. You'll be notified via email when the recording is available. Now let's meet today's presenters. David Tremblay is a chairperson of the Ethernet Alliance, and he works as a system architect at Aruba, Hewlett-Packard Enterprise's networking division. Here he is a Power over Ethernet subject matter expert, leading cross-functional consensus building for new product opportunities and driving networking technologies into multiple HPE product organizations. Next, we have Mike Sandijk, who recently joined On Semiconductor as a product marketing manager and has long-standing experience within the electronics industry. With a past in industrial automation and IoT applications, switching with engineering support and product marketing of semiconductors, he couples an acute business sense to advancements in technology. Then last but not least, Joris Lemailleux is an applications engineer in the energy management business unit at On Semiconductor. He is a specialist in Power over Ethernet products and solutions and plays a pivotal role in certification testing on the Ethernet Alliance PoE subcommittee. And now, without further ado, we will start our webinar.
Hello and welcome to the Power over Ethernet and Connected Lighting webinar, brought to you today by Ethernet Alliance and On Semiconductor. On the agenda today is an overview of Power over Ethernet in the market, followed by a technology session concentrating on lighting and visual light communication. Next up is a deep delve into the Power over Ethernet technology by Joris Lemailleux, our application engineer, rounded off by an overview of the available products from On Semiconductor for Power over Ethernet and visual light communication.
Hello, everyone. My name is David Tremblay, and I'm the Ethernet Alliance Power over Ethernet Certification Chair. Today, I'm going to provide a brief overview of the Ethernet Alliance mission and its strategies. Then I'm going to jump right into Power over Ethernet devices, market confusion, and finally ending with the PoE certification program. The Ethernet Alliance is a global community of end users, system vendors, component suppliers, and academia. Our mission is to promote the existing and emerging IEEE 802.3 Ethernet standards, to accelerate industry adoption, and to demonstrate multi-vendor interoperability. Here's a quick overview of our current membership, including our principal members and participating members, and finally associate members and consulting members. As you can see, we have a pretty wide range of corporate members as well as academia, including college campuses. The Ethernet Alliance strategy is to constantly look to expand the Ethernet ecosystem and supporting Ethernet development activities. We accomplish this through a variety of hosted activities, including test events, thought leadership forums, and producing educational content that is distributed through worldwide marketing channels. We also produce an annual technology roadmap, which can be downloaded from our website. The current version is the 2020 roadmap, and we plan to update the roadmap shortly to show the technology advancements for 2021. So you may be wondering which devices in the market are actively utilizing Power over Ethernet technology today, and what we might to expect from PoE devices in the future. What I'd like to share with you is a survey that the Ethernet Alliance completed back in January of 2020, and we surveyed 822 users. 48% of those were system installers and integrators, 30% of those were end users, and 14% were designers. The rest were made up of various consumers and academia. Virtually everyone that we surveyed was installing and using PoE today. As you can see from this map of devices, we have Wi-Fi access points as taking the largest segment, followed by cameras, phones, and the various other segments listed. The lighting segment is by far the largest growth segment that we see today, and we expect that segment to continue to rise in the future. There are a lot of different varieties of PoE out in the market, some standardized and some not. As you can see from this slide, there's a fair amount of PoE confusion in terms of what are all the different standards, what do they mean, what are the different classes of wattages, what are the different types, how do I know if power is being delivered over 2 pairs versus 4 pairs, and then the various marketing names used to describe PoE, like PoE, PoE++, UPoE, and then there's passive and LLDP negotiated implementations. So you might be wondering, how do I know what is PoE, what is not, and how do I know what's going to be interoperable with each other? So the Ethernet Alliance and its members released 2 generations of Power over Ethernet certification programs, offering a rigorous test bed based on IEEE 802.3 PoE standards. The passing products can display a trademark logo similar to the 2 sets of boxes shown here in the center of the screen. And these boxes are used to easily identify the Power over Ethernet capabilities of a power source equipment, or PSE, as well as a power device, or PD. All certified products are listed on a public registry for easy lookup. The EA PoE certification program makes it easy for all users and installers and system integrators to quickly identify standardized PoE products and ensure the highest level of interoperability once deployed. This concludes my portion of the webinar, and I thank you for your time. Please feel free to visit us on our website and contact us if you have any questions. Thank you.
Now we start delving a little deeper into the power of Ethernet and lighting technology. The first part is a short introduction on connected lighting and visual light communication. Connected lighting is one of the fastest growing segments in the power over Ethernet application market. With a drive to smarter building management, more efficient use of power, the integration of lots of sensors into the luminaries, this is a fast expanding market. Visual light communication is an optical communication technology being used more and more today. Actually, photophone work at Bell Labs predates radio. You can think of visual light communication as an amplitude modulation, where the visible light is used as carrier and the information is modulated on top of that with the brightness. This is usually a unidirectional communication in low data rates in the kilobits per second. Not to be confused with Li-Fi, which achieves higher data rates, but is usually a bidirectional communication method. As we will touch on this later on in the presentation, here is an overview on what exactly is yellow dot. Yellow dot is an indoor positioning technology. Each LED ballast has a unique identifier that indicates its position within a building. The LED ballast signals through visual light communication to a receiver, which can be a phone, tablet, things like that. The phone's camera detects the code and reveals the position within the building. With triangulation between LED fixtures, the accuracy is within centimeters, with far higher accuracy than is possible with today's radio frequency methods. Certification for the yellow dot trademark requires passing a range of tests. And yellow dot works on two defined data rates, 1 kilobit per second and 2 kilobit per second.
Hello, my name is Joris Lemayeux, and I'm the application engineer and specialist in Power over Ethernet products, and I'll guide you through the technical details of and how to implement a PoE solution. Power over Ethernet, or short PoE, is a technology that already exists during almost 20 years, and its main benefit is that it allows you to deliver power next to data over existing Ethernet cables. In September 2018, the 802.3bt standard was approved, and this new standard will allow you to make a system that is powered over the Ethernet with a lot more power capability, up to 90 watts. So with this new 3BT standard, a lot of new applications will be possible. First, I'd like to begin with an introduction to Power over Ethernet, because before telling what it's new, it's important to know what the basics are, as those still hold. So, how does a Power over Ethernet system look like? First of all, you have a certain device that you want to power over the Ethernet cable, and that device in terms of Power over Ethernet is called a power device, or a PD. Then you have the Ethernet cable. This is just a regular Ethernet cable that is used for data that can be used to transfer power as well. Of course, you still need a power source, and in terms of Power over Ethernet, this is called the PSE, which is short for Power Sourcing Equipment. The PSE incorporates an AC-DC converter, and the PSE will be powered from the mains, so you'll need a mains power cable as well. So a PoE system consists out of just these four components. A Power over Ethernet system is easy to set up and use because it's a worldwide standard that guarantees interoperability. Moreover, PoE is safe and easy to deploy. Now I would like to focus on how PoE works. How actually is the power transferred from the PSE towards the PD over the Ethernet cable? The Ethernet cable that's used is a regular Cat5 or Cat5e cable. As you know, an Ethernet cable actually contains 4 twisted pairs. The power is basically transferred over 2 twisted pairs, and there are 2 modes that can be used. The first mode is called alternative A. In that case, the power is transferred over the same pairs that are already used to transmit and receive the Ethernet data in a 10 base T or 100 base TX Ethernet system. Of course, the question that pops up is, how is this done? Because how can you combine power and data? The trick here is that the power is transferred between 2 pairs in a common mode kind of way with respect to a data pair, whereas the Ethernet data is differential within a data pair. In this mode, the means to inject and extract the power on to and from a data pair is to use the center taps of the LAN transformers. And so, you can combine power and data. The second mode is called alternative B. In that case, in a 10 base T or 100 base TX Ethernet system, the power is transferred over the spare pairs that are not used for transferring the Ethernet data. Then you can inject and extract the power directly onto and from a pair. But it's also possible to use PoE in a gigabit Ethernet system, and then also on alternative B, the center taps of the LAN transformers will need to be used. So now we know how the power is transferred. What are the power characteristics? The power supply in the PSE is basically a DC voltage source. The voltage level is around 54 volts, so a bit above the more common 48 volt, because a higher voltage results in a higher power transfer efficiency over the Ethernet cable. But still, the voltage remains below 60 volt for safety reasons. The maximum voltage according to the PoE standard is 57 volts. What's good to know is that you can use power over Ethernet over a distance up to 100 meters. Of course, 100 meters of cable has a significant resistance, and the worst case cable loss is taken into account in the PoE standards. Therefore, the power rating of the PSE and the power rating of the PD will be slightly different. The power rating that will be used here during this presentation will typically be the power level at the PD inputs. The first PoE standard, referred to as 802.3AF, allows up to 13 watt of usable power for the power device. The update of the first PoE standard, referred to as 802.3AT, increased the usable power level up to 25.5 watts. The new PoE standard, referred to as 802.3BT, is also a new generation, and it further increases the usable power level up to 71.3 watts, and that's again for up to 100 meters of cable. But eventually, for a short cable, up to 90 watt is possible. Overall, that's really a significant improvement over the previous generation. You still have to take into account that there will be some losses due to the DC-DC conversion in the PD. So when designing a PD system, the actual power that can be used for the application is given here in the table on the right for 90% efficiency. Of course, you can increase the power value up to the PD input power by using a higher efficiency DC-DC converter. What's important to know when designing a power over Ethernet system is that the current and the power are limited. The PSE will accurately monitor the current and/or the power consumption. You must design your PD system so that it never goes beyond the power constraints, because otherwise the PSE will disconnect your PD, which is not wanted in any case. The power is not immediately applied to the PSE output, because that would not be safe and could give issues. Not every Ethernet device can withstand around 54 volts between two pairs. The PSE needs to follow a process, kind of an algorithm, before it can power up a PD. The first step in this process, which is called detection, is crucial for the reliability and safety of Ethernet systems. During detection, the current is limited to 5 milliamps and the voltage is limited to below 10 volts, which is really safe and cannot destroy a non-PoE device. Basically, detection is an impedance measurement performed by the PSE. The PSE measured the incremental impedance by applying two different voltages sequentially and measuring the corresponding currents. A power device that requests power will present a 25 kilo-ohm resistance towards the PSE. So if the incremental resistance is close to 25 kilo-ohm, the PSE knows that it's a PD that's connected. A PD can also know that just a regular Ethernet device is connected that's not PoE capable. In that case, the PSE will either measure a short or a termination resistance in the range of 150 ohms. Then the PSE knows that it's not allowed to apply power to that Ethernet device. A PSE can also know that no device is connected, because in that case, the PSE will measure a very high impedance. When the PSE has detected a power device, it goes to the next step in the process, which is called classification. As we've already seen before, there are different power levels that are possible. It's important to know that both PSE and PD have a mutual understanding of the maximum power level that is allowed in the application, because if the PD goes above the power budget of the PSE, it will result in a disconnect, which is of course something you do not want. In general, for PoE, there are now in total 8 classes that are defined. In the tables, you can see what the different power levels are that correspond with those 8 classes. So going back to the first PoE standard, the power class went up to class 3 with 13 watt of power that was available to the power device. The update of the first PoE standard introduced the concept of class 4, which allowed the power level to go up to 25.5 watts. And now, in the 3BT standard, you can go up to class 8, which means a power level up to 71.3 watts. That's for 100 meters of distance, but eventually can go up to 90 watts for short distances. Next to class 8, the 3BT standard introduces 3 other new power classes. Class 5, Class 6 and Class 7 that correspond to 40, 51 and 62 watt respectively. During classification, the PSE will probe what the maximum power is that the PD would need for its operation. If you implement a power device that requires more than 13 watts, so class 4 and up, you are not sure upfront that always the appropriate PSE will be hooked up to your device. So it's important to know that a power device that requires more than 13 watts can also be powered up in what's called an underpowered state. This table shows you what the fallback classes are. The requested class will always be fixed for your design, so you only need to look at a few rows in this table. If, for instance, you would request class 8, you can indeed get assigned to class 8 and then you have your full power capability. Actually, you could likely be forced to operate in class 6, class 4, or even class 3 only, and in that case you should at least indicate to the end user that you are underpowered, so he knows that he should connect the device to a higher PSE in order to have the full power capability. Still, you will need to remain within this lower power limit in order not to cause a disconnect by the PSE without the user knowing what is wrong. Again, if you only need up to 13 watt, so for class 3 and below, you do not need to worry about being underpowered, because then you're sure to have the requested power if you have been powered up. Now I'll give some more background on how classification actually works. It's kind of a state machine that's executed. When the PSE increases the voltage to the class event voltage, which is around 18 volts, the PD will actually draw a specific amount of current that is in correspondence with the requested class or the power level that the power device would like to have. The first and third pulse are just for allowing the PSE to probe the power level of the power device. By applying a second pulse, the power level is increased. The same is the case with a fourth and a fifth pulse that's given. By counting the number of pulses that have been applied by the PSE, the PD actually knows how much power it is able to draw. Next to the maximum operating power level, there is now also additional information that is exchanged with the 3BT standard. The second thing that is exchanged from a PSE to a 3BT power device is the minimum amount of current that the PD needs to draw in order not to be disconnected. So remember that Power over Ethernet has, besides a maximum power level, also kind of a minimum operating current, referred to as MPS. A minimum operating current makes sense, because if you would unplug the Ethernet cable, you do not want the 54 volts to remain present at the PSE output. Otherwise, a PSE might still damage a non-PoE capable Ethernet device that is connected afterwards. Therefore, a PSE will continuously monitor the current to check whether the power device is still present, and if not, disconnect the power. The third thing that is 3BT power device now can exchange towards a 3BT PSE is if it supports Autoclass. Autoclass is a new feature in the 3BT standard, and I will go into further detail later on. Only when the detection and classification stages have finished successfully, the PSE will apply the full voltage, so around 54 volts, onto the Ethernet cable to actually power the PD. Then the PD will have the full voltage at its input, whereas the input capacitor of the internal DC-DC converter at the other end of the pass switch is still discharged. The PD controller contains an Inrush circuit that will charge the input capacitor in a controlled manner, meaning that the P current remains below the Inrush current limit imposed by the PSE. When the input capacitor is charged, the PD controller will give a power good signal to the adjacent DC-DC converter, and then the complete PD system can actually start. There is one more thing to consider. Initially, during Inrush and power delay, the power level is still limited to class 3. It's only after 80 milliseconds that the PD can go to the power level beyond class 3 it has been assigned to by the PSE. So to wrap up what happens when you connect a power device to a PSE with an Ethernet cable, this diagram shows how the voltage and the current waveforms would look like. So first the PSE will be in the detection stage where it will apply two voltages. There will be two corresponding currents from which the PSE can calculate the incremental resistance and detect the presence of the PD. Then the PSE will go to the classification stage. You will see a number of pulses which will then correspond to the power class assigned to the PD. Then the PSE will power up the PD by applying the full 54 volts. Then the PD will go into Inrush and charge its input capacitance. When the capacitance is charged, the system will start up. The microcontroller will need to check what the power class is the PD has been assigned to, and control the system as such that it will only go to the maximum power level according to its assigned class. This was the basic introduction of how Power over Ethernet works, and I would now like to highlight the new features and capabilities of the 802.3bt standards. So, what's basically new with the 802.3bt standards? In the previous generation of PoE, it is only allowed to use 2 pairs to transfer the power. Now, with the 3BT standard, it's allowed to transfer the power over all 4 pairs, so both modes or both alternatives can be used at the same time. For 802.3bt, they did a further detailed analysis of how much current can actually be transferred over an Ethernet cable. First of all, it's possible to use both modes simultaneously at the previously rated current, which already doubles the power budget. Furthermore, it's even possible to increase the rated current level of each mode. Then finally, by fine-tuning the system with a slightly higher minimum PSE voltage, the power budget can be further increased slightly. When you combine those 3 measures, it results in a 3 times higher power level that can be delivered by the PSE. So instead of the 30 watts we now have in the previous generation with 802.3bt, we can go up to 90 watts. So what are the benefits of 802.3bt? Of course, most important benefit is the higher maximum power level that's possible. This will enable the implementation of a lot of new systems that can now be powered by PoE. It will also increase the efficiency, because by using all 4 pairs, you can actually lower the effective cable resistance, which of course results in a higher efficiency power transfer. It also allows for a lower standby power. Now the standby power can be lowered to around 13 mW for up to class 4 and down to 20 mW for higher power levels. Finally, it will also allow better allocation of the PSE power budget of a multi-port switch. This is the new feature Autoclass that I will talk about now. This is an example of the use case of Autoclass. As I told before, a PD needs to request a certain power level. If, for instance, the PD would need up to 42 watt at its input, it needs to request 51 watt, which is class 6. On the other hand, the PSE needs to allocate 60 watt to be able to power this class 6 PD over an Ethernet cable of up to 100 meters. But now, when both the PD and the PSE support Autoclass, the PSE can actually measure the maximum power the PD requires. As a consequence, the PSE only needs to allocate around 44 watts to power this PD here. The benefit of Autoclass becomes more clear when you would need to power 8 of such PDs. When using Autoclass, the multi-port PSE would only need a 350 watt power supply, whereas without Autoclass, the multi-port PSE would need a 480 watt power supply. From system point of view, Autoclass can give you significant cost savings. These are some typical applications where PoE and the new 3BT standard can be used. One example are pan-tilt zoom IP cameras incorporating motors and eventually heaters. Another example is connected lighting, lighting systems that enable smart buildings. Then to wrap up, I would still like to quickly show you how to actually implement PoE on your new products, how to select the appropriate PD controller. These are the 5 steps you basically need to go through when designing your system. First of all, you need to determine the maximum power level that you will need in your application. As you know, there are 8 power classes defined in Power over Ethernet, and you need to choose a requested power class for your system. Next, you need to gather some additional information. Here, I just would like to highlight the isolation requirement of an Ethernet system. You need to take into account that the Ethernet lines always need to remain isolated with respect to ground or earth. If you have a floating system, you could use a non-isolated DC-DC converter. This is typically the case in connected lighting. But this is kind of an exception. In general, an isolated DC-DC converter is usually required. Then I will finish my presentation with some additional information. Here on this last slide you can find some important links for further reading about Power over Ethernet. We now reached the end of the presentation. I would like to thank you for your attendance.
For the final part of the webinar, we give an overview of products available from ON Semiconductor in these applications. To demonstrate our capabilities in the lighting market, we released the ON lighting platform and have launched a new advanced LED driver. The ON lighting platform has a modular approach. Here showing a 4-board assembly with the Power over Ethernet power interface, dual LED driver, dual LED string, and the Bluetooth control board. There is also an AC/DC powered option available with a power factor corrected flyback setup. The Bluetooth control board allows control of the setup through an application where you can read back the system currents and voltages, control the LED strings through the PWM channels, and see which power class has been negotiated with the Power over Ethernet power supply. The NCL31000 is an advanced LED driver. It combines system power, LED driver, and metrology block into one integrated IC. With a high efficiency LED driver, 2 DC-DC converter blocks, one fixed at 3.3 volt, and one adjustable between 2.5 to 24 volt. So the entire system power can be generated with the one driver. It is visual light communication capable and yellow dot ready, and has a very linear high bandwidth dimming input, allowing dimming down to 0. With several other features like active fault protection and diagnostics, embedded measurements through the metrology block, fairly elaborate, and spread spectrum options to reduce conducted EMI. The driver is capable of driving luminaries up to 150 watts depending on the input power provided. The NCL31000 has a high input voltage range, making it ideal for Power over Ethernet applications. In a system setup, as in the example here, using the NCP1095 as the Power over Ethernet interface, followed by the NCL31000 driver powering the complete system, and of course controlling and powering the LED string. The dynamic current is maximum estimated around 2.8 amps, taking the current ripple into account, making it possible to drive luminaries up to the 130 to 160 watt range, depending on the input power. Some key specifications for the NCL31000 are its compliance with the IEEE standards, paired of course with the appropriate Power over Ethernet interfaces, its linear and deep dimming capabilities, visual light communication, possibilities, 2 serial options, and an advanced LED driver on board, of course, with high efficiency, 2 DC-DC converter blocks, spread spectrum capabilities to reduce EMI, and last but not least the power metering with a fairly high accuracy, monitoring voltages and currents within the system, temperature protection, and an accurate voltage reference. As the final part of the webinar, we present the Power over Ethernet power device products from ON Semiconductor. ON Semiconductor is one of the key contributors to the new generation certification test protocols. We're one of the 4 semiconductor companies actively defining these new certification tests to ensure interoperability between all Power over Ethernet equipment. With the certification tests also come new logos to indicate certified equipment on the power device side, indicated by an arrow going into the system, or the power supply equipment with an arrow leaving the system, and the number indicating the power class of the device. Recent certifications from our products is the NCP1090 and 1094, which have been certified for Class 3 and Class 4, and we have several other devices now under certification as well. The NCP1081 and 1083 are the first set of devices in our range. These go up to Class 4, which according to the standard has a maximum of 30 watts. And as you will notice, with all of our devices, there is ample power headroom. Most notably, these 2 devices have a DC-DC converter built in, so you can make a very compact design with these. There's a programmable classification current, Inrush current limit, an operational current limit, adjustable under voltage lockout, temperature protection, and notably a hot swap pass switch integrated as well. The difference between the 1081 and 1083 is that the 1083 also offers an auxiliary supply option. The NCP 1090, 91 and 92 are simple interface controllers, meaning they do not have the DC-DC converter on board, meaning they also offer more flexibility in the design topology. These go up to Class 3, 15 watts according to the standard, so again, ample power headroom. Here again also programmable classification current, Inrush current limit and operational current limit. The difference between the devices is that 91 offers the adjustable under voltage lockout and the 92 offers the auxiliary supply option, where the 90 is the simplest device without these options. In the same range, the NCP 1093 and 94 go up to Class 4, extending this range in power capabilities. Again, these are interface controllers without a DC-DC converter on board, so offering again more flexibility in the design. With the same capabilities and a hot swap pass switch on board. With the difference between the 2 devices, again, with the adjustable under voltage lockout or auxiliary supply options. At the top of the range, we find the NCP 1095 and 1096. Again, interface controllers going up to Class 8, the new standard, with 90 watt maximum. Classification is taking care of, again, flexible currents. Under voltage lockout and protections are integrated. And the difference between the two devices are the integrated PASFET in the 1096, whereas with the 1095, the PASFET is external, as for example in this schematic. In the continuous effort to improve efficiencies in the overall application, we have looked into from which point it starts to make sense to switch from simple diode bridges to a diode plus MOSFET bridge or a completely active bridge, the details of which you can read in these technical notes mentioned here. But as you can see from the graph, really from class 4 onwards, meaning around 15 watt, it really starts to make sense to look at other bridge topologies. And certainly in the higher power classes, an active bridge makes the most sense. Continuing on the topic of efficiency, the NCP 1096 has a very low on-resistance for the PASFET. This allows us to achieve a very high efficiency in pass-through, meaning the power that is passed from the power over Ethernet cable to the application behind it, reaching an efficiency of 99.2%. Looked at it from another perspective, with heat imaging, we can see that the temperatures reached within the application stay within very reasonable levels. Finally, to round off, we have two product selectors. This one is constructed around the maximum power that you would need to achieve in your application under worst case conditions, the theoretical power that is achievable by power over Ethernet class, minus the connection and line losses worst case, and taking 10% DC-DC converter loss into account. This is the power that you could, under worst conditions, achieve with that power over Ethernet class. Next to it are listed the devices according to the options that they have, where you can choose from to achieve this in your application. And last but not least, the more traditional product selector with all the devices listed according to their power capability and the integrated features. Starting with the NCP 1090 to 1092, the interface controllers going up to class 3, the 1093 and 1094 equal interface controllers going up to class 4, the 1081 and 1083 with the integrated DC-DC converter, and topping off the range, the 1095 and 1096 going up to class 8, 90 to 100 watts, with either the integrated FET or not.
Thank you all for the excellent presentations. We will now start our Q&A session with Mike Sandijk and Joris Lemailleux. During the presentation, we have received a number of questions, so we will jump right in. If you would still like to submit any questions, just type your question into the chat box on your right. So, first question. Are the on-semiconductor power over Ethernet PDs compatible with other suppliers' PSEs? Mike, Joris, yes.
Yes, they are. We've run several tests comparing which devices are compatible. We have measurements from the lab on that, so these can be consulted. And most of our devices adhere to the standard and have been, some have already been certified, some are in certification.
Thanks, Mike. Another question, from which point would an active bridge be advisable for power over Ethernet?
As we've seen, this starts from around about 15 watt up there to make sense, depending a little on the system requirements. But from 15 watt and upwards, it starts to make sense if you want to reduce standby power to look at other bridge topologies.
Thank you, Mike. Then one last question. Are the on-semiconductor power over Ethernet PDs HD-based T compatible?
Yes, they are, but it's an either-or situation. So either it's configured to be Power over Ethernet compliant, or it's configured to be Power over HDMI compatible.
Okay, thank you, Mike. So these are all the questions we have time for today. If you didn't get to your question, we will follow up through email. So on behalf of On Semiconductor, I would like to thank everyone for attending, and I wish you a nice rest of your day. Thank you.
Thanks. Bye.
Bye.